Okay, so now we're going to get into chapter 9. And in chapter 9, we'll be dealing with that area in chemistry, oftentimes referred to as stoichiometry. And as we're going to see later on, stoichiometry is that area in chemistry which deals with the quantitative relationships between substances involved in a chemical reaction. So these are calculations which, of course, would have to be based on a chemical equation accurately representing that reaction. So in order for us to get into this, let's review a couple of things that we met before. Remember this term, molar mass? This is, by definition, the mass in grams of a substance in 1 mole. And numerically, it is the same thing as the atomic mass. And as I said before, the difference between the atomic mass and the molar mass is that the molar mass is expressed in units of grams per mole, but the atomic mass is expressed in AMU units. Remember what the mole represents. The mole represents the amount of substance which contains Avogadro's number of atoms, elements, molecules. In the case of elements, it would be atoms that is present in 1 mole. All right, so there's a relationship between 1 mole and the mass, which is the molar mass, and there's a relationship between the mole and the number of atoms, which would be Avogadro's number. All right. For a compound, the molar mass would be the sum of the molar masses of all its atoms according to the formula. All right, so we talked about that before. And here's a relationship, a mathematical relationship between the molar mass and the mass of an element, specifically a monatomic element. The molar mass would be equal to the grams of that element divided by the moles of that element. And the molar mass of a substance would simply be equal to the grams of that substance divided by the number of moles of that substance. All right. And of course, we know the relationship between moles, Avogadro's number, and the number of molecules or atoms or ions. The number of moles will be equal to the number of molecules divided by Avogadro's number of molecules per mole. Okay, so as we said before, the mole basically is the linchpin relationship between Avogadro's number and the molar mass. All right, now for calculations involving mole, mass, and volume relationships, the equation must be balanced. All right, and what do we mean by that? Basically, what that means is that the equation must accurately represent the fact that the law of conservation of mass is governing the reaction. In other words, nothing is being created nor destroyed. So if you look at this particular example right here, the reaction between aluminum and iron free oxide to form iron and aluminum oxide, in order for this equation to be balanced, we need coefficients of 2 and 2 here before the aluminum and the iron, so that when you do a count of all the atoms on both sides, you'll find that they're equal. So you have 2 aluminum atoms here. This subscript 2 makes this 2 aluminum atoms on the right side. You have 2 iron atoms here. You have 2 iron atoms here. You have 3 oxygens here, 3 oxygen there. So therefore, that equation is balanced, right? Now, whenever we're balancing any equation, we must only adjust the coefficients. We cannot change the subscripts in the formulas, because by changing the subscripts, you're basically on paper changing the substance into something else. So whenever we're balancing equations, we have to make adjustments only to the coefficients. And that's why I recommend that students do this using pencil and paper, so that you can erase coefficients when necessary, because invariably, especially for the more complex equations, sometimes you would place a coefficient in front of a substance and then you find out later on that you have to erase it. All right, so I would recommend that you use pencil and paper to balance equations, and then when you write down your final answer, you can do it in ink. Now, the thing about a balanced equation is that it reflects not only what happens at the microscopic level, but also what happens at the molar level. So in one sense, you can look at this equation and say, well, what this equation means is that 2 aluminum atoms will react with 1 formula unit of iron free oxide to form 2 iron atoms and 1 formula unit of aluminum oxide. All right, so that's one way of interpreting this equation. But you can also interpret it in terms of moles, as you can see in this line right here. In other words, you can say, based on this equation, based on the coefficients that are present before the different substances, that 2 moles of aluminum will react with 1 mole of iron 3 oxide to form 2 moles of iron and 1 mole of aluminum oxide. All right, and it is that relationship that we exploit whenever we're doing calculations involving stoichiometry. All right, okay, so now we're going to first define stoichiometry, which I stated already. It is that area of chemistry that looks at the quantitative relationships between reactants and products. Another definition you need to know about is a mole ratio. The mole ratio is basically the ratio between the moles of any two substances involved as reactants or products in a chemical reaction. And these coefficients are derived, the mole ratio I should say, are derived from the coefficients that are used in the balanced equation. So for example, if you look at this equation, which is already balanced, right, then you can basically write down a mole ratio, which represents the relationship between any two of these substances. So for example, you could look at the relationship between the nitrogen and the hydrogen. That's a 1 to 3 mole ratio. You can write it like this, or you can switch it up. You can have the moles of hydrogen above and the moles of nitrogen below. So that's one example of a mole ratio. All right. And another example, you could look at the relationship between the hydrogen and the ammonia. That's a 3 to 2 mole ratio, or the other way around, 2 moles of ammonia to 3 moles of hydrogen. In other words, you could flip this fraction to get another conversion factor, which represents the relationship between the hydrogen and the ammonia. All right. So those are just two examples, and that is what you use in stoichiometry. We use these mole ratios to convert the number of moles of one substance to the corresponding number of moles of another substance in a stoichiometric type problem. All right. So this underscores the importance of having a balanced equation to begin with, right? If the equation is not balanced, more than likely that means that you have the wrong coefficients, and therefore if you use those values, then it is very possible that your resulting calculations will be wrong. So as stated here, the mole ratio that is used, the mole ratio is used in every type of stoichiometric problem, and therefore it's important that you start off with the right mole ratio, which means that you need to start off with a correctly balanced equation. So what is involved in the mole ratio method? Well, the first step, if necessary, is that you convert the quantity of the starting substance to moles. All right, so you may be given a problem where you're given a certain amount of a substance in grams. The first step is that you'd have to convert the grams to moles. Now, in some questions, you may be given the moles already, which means that this step is not necessary. But in other cases, you could be given a mass in grams, and therefore you'd have to convert to moles. All right, so as stated here, so that's step one. Step two, you have to convert the moles of the starting substance to the moles of the desired substance, and this is where the mole ratio comes in from the balanced equation. All right, and then step three, you have to convert the moles of the desired substance to the units specified in the problem. So again, you might be given a question where you're asked to determine, for example, the mass of a substance, but after doing steps 1 and 2, you end up with the moles of that substance. Then the next step, if required, is that you convert that to whatever the units. So it could be asking for grams, you'd have to convert from moles to grams in that case. All right. Okay, so we're going to go through these steps in more detail. So as I said before, the first step, if necessary, is where you convert from grams to moles, and this is how you do it. You take the mass in grams and you multiply by this conversion factor where you have 1 mole of the substance as a numerator and the numerical value of the molar mass down here as a denominator, and the grams unit will cancel out here, and you're going to end up with your mole unit as your final answer at that point. All right, so we know how to do this already. Here's an example. Let me just do this example quickly. So basically in this example, they gave you the mass of sodium chloride, and let me see here. So the mass of sodium chloride is 292 point, okay, what's going on here? 215 grams, and Fortunately for us, they gave us the molar mass of sodium chloride, so we don't need to worry about calculating it. So this is NaCl, and you're going to put 1 mole of NaCl here as a numerator, and down here the molar mass, which is given 58.443 grams of NaCl. That goes with that, and when I do my number crunching, 292.215 divided by 58.443, the answer I get here is 5.000 grams, moles of NaCl. All right, so we all know how to do that. That's basically how we determine the moles if you're given a mass. All right. Okay, the step 2 in this process is that we determine the mole ratio of the required substance or desired substance to the starting substance. So, of course, that is based on the coefficients in the balanced equation, right? The number of moles of each substance in the balanced equation is indicated by the coefficient. And we use these coefficients to set up the mole ratio. So, therefore, the mole ratio would be the moles of the desired substance in the balanced equation divided by the moles of the starting substance in the balanced equation. All right. So that's basically what we do in step 2. And then we multiply the number of moles of the starting substance from step 1 by the mole ratio to obtain the number of moles of the desired substance. So we kind of set it up like this. So once we establish the mole ratio here, then we multiply the moles of the starting substance by this ratio, and that will give you the moles of the desired substance. All right. And then, so now we can apply that to this particular example. So let me turn on the pen here. All right. So in this case, they gave you the balanced equation, which is not necessarily going to be the case, right? You could be given an equation where you're asked to balance it. All right, so in this case, we don't have to worry about that. They gave us the balanced equation, and the question is asking for the moles of lead 2 chloride if 5.000 moles of NaCl react. So this is the number of moles of sodium chloride that we calculated earlier, and the question is asking for the moles of lead 2 chloride. All right. So we start off with the 5.000 moles of NaCl, and we multiply that by the mole ratio from the balanced equation. So what's the mole ratio? Well, if you look at the balanced equation here, you see a coefficient of 2 here and a coefficient of 1 here. So therefore, you're going to put 2 moles of NaCl down here and 1 mole of PbCl2, and this will be equal to 2.500 moles of PbCl2. And that's how that is done. All right. So that's step number 2. And in step number 3, it says you're going to calculate the desired substance in the unit specified in the problem. So as I said before, the question could be asking for the answer in moles, in which case you just stop at step number 2. But if the question is asking for the answer in, let's say, grams, then you'd have to do the conversion from moles to grams, right? So for example, well, this is a setup actually. So basically you take the moles and you multiply by the molar mass of the required or desired substance, and that give you the grams. You could also be asked to calculate, like for example in this case, 5.00 moles of water. You multiply by the molar mass to get the mass in grams of water. You could also be asked to calculate the number of atoms, in which case you'd have to multiply the moles by the Avogadro's number. So for example, if you get 5.00 moles of sodium atoms at that point, then you multiply by Avogadro's number to get the actual number of atoms. All right. So it all depends on what the question is asking for. If you want to get a number of molecules, again, it's the same thing. I think I showed you this one before, so let me skip that. All right. So that's where we're going to stop for today. The next video will deal with mole to mole calculations. Until next time.